We have defined continuity of functions between spaces x and y. So let's look at a function x and y. But that is sometimes inconvenient because it is too global. And what we know is how the function behaves near a point. If one goes back to sum of functions or products of functions from real to reals in analysis and so on, controlling at a point was much easier, and in the more complicated examples, say constructing a boundary at infinity in set topology, this will be even more so. So we'll look at some local aspects of continuity here. So suppose we just have a function, then we'll say f is continuous at x naught in x if we want to give the epsilon delta definition, but there are no epsilons and deltas. Instead, there's an x naught and an f of x naught, and as usual. But what we have are open sets, and the inverse image of an open set was the definition of continuity. But what about continuity at a single point? It is like an epsilon delta. We take an open set containing f of x naught, okay, this black region, then there must be an open set here which maps into this. We can't ask for more because you can be continuous at a single point but no other point in its neighborhood. Okay, so this is open sets will play the roles of the unit balls, or mod x minus a is less than epsilon and delta, etc. So if given v contained in y, open such that, of course, f of x0 is in v, there exists, let's say, w contained in x, open, such that x0 is in x and not in x. Of course it's in x, that's true, but that's not having any information, such that x0 belongs to w and f of w is contained in v. Okay, this is just like epsilon delta, except we are using open sets. Okay, so recall, so w is, or wv are neighborhoods of x0 and f of x0 respectively. So the point is that what we are doing is we are looking, neighborhood for us is an open set that contains the point. So given a neighborhood of f of x, there's a neighborhood which maps into this. That's what we want to say. Okay, so you would expect that continuous at every point is continuous, and indeed that is the case. F is continuous if and only if for all x0 in x, f is continuous at x0. Okay, so first of all, let's see the direction where f is continuous. Suppose f is continuous. We want to show it's continuous at every point. And let's pick a point. So we'll pick a point x0x, and we have this set which was called v, and v contained in y is open with x0 in v, f of x0 in v. Then it's easy, we just take the inverse image. Then w, which I'll define as f inverse of v, contained in x is open, x0 belongs to w, and f of w is f of f inverse of v. Well, it's actually contained in v. It may seem like f of f inverse it has to be equal to v. It's not the case. This is not an invertible function, because if something is not in the image of f, okay, so y is just the codomain, so if it's not in the image, then we take its inverse image, it will be empty, so you won't get it back. But in any case, f of w is contained in v is by definition, so as required. So w is as required. And the converse is slightly cleaner version of what we did with metric spaces, because we don't need to switch things here. Okay, so the conversely, suppose we have x0 and f of x0. Yeah, where was that? Yeah, so conversely, suppose f is continuous at x0 for all x0 in x. Now we want to show f is continuous. We show f is continuous. Now this is quite similar to what we have done before. So it's a good thing that, as von Neumann said, in mathematics you don't understand things, you get used to them. So the same pattern means you'll get used to what we do. So we want to show that, so let V contained in Y be open. And let's give it a name. Let's call it W equals F inverse of V. Okay. So to show now, maybe I wouldn't call it W because I've used W's for neighborhoods of points, but some Q or something. So to prove, what we have to prove is Q is open. Okay. So let X, so let's prove it. So let's pick a point here first of all. Let X0, because that's where we have the definition. Then there exists W x0. I'm going to label it by the point, and to avoid double subscripting, let's just call it x. Let Wx in. So let x belongs to Q. That means f of x is in V. So we are going to take V in this definition. That is, V is the open set containing f of x. So this implies that f of x is in V, remember. So then there exists Wx contained in V open. I'm sorry, in X open. X is in Wx such that, so Wx is an open set, X is in Wx such that f of Wx is contained in V. Okay. So now claim is that Q is union of X in X. Okay. So by the way, this implies that Wx is contained in Q. Because if f of Wx is contained in V, then any point here goes into V, so it's that point is contained in inverse image of V, which was Q by definition. F inverse of V. Okay, so we have open sets. So the claim here is that Q is exactly union over all X in Q of Wx. And note that this is open because this is a union of open sets. Okay. And then we just check the two-way implications. Q is contained in so in this union X in Q Wx, as X belongs to Q, implies that X belongs to Wx. Okay, so maybe I should say X naught belongs to Q, implies X naught belongs to Wx naught, and Wx naught is contained in the union X and Q of Wx. And conversely, as Wx is contained in Q for all X, union X and Q of Wx is contained in Q. Okay, so what we did is rather simple. I went through it rather formally, so we'll take a picture for completeness. So here is an open set V inside Y. Y is the biggest set. Here is X. Here's an open set, and we want to look at the inverse image of it. It is some set like this, and what we want to show is that it is open. And the idea is that this is a neighborhood of every point in it. Okay, so if I take any point here in the inverse image, look at its image, V is a neighborhood of that, and so by definition of continuity at that point, we can find, think of it as an open ball, an open set here, Wx, which contains this point and whose image is contained here. So the set itself is contained in this set Q. So the big inverse image set was Q. Okay, and so Q is the union over all points of these open sets, so it's open. This is the proof of continuity. So we have seen a nice local criteria for continuity.